Okay, sorry we're late getting started, but let me make one kind of announcement. I don't know if you've been following the pattern of the term so far, but so far this term, I try to take all the chances I have, take advantage of the time I have to get papers graded on Tuesday and Thursday. I don't have any time on Monday, Wednesday to grade, to speak of. I got in a little early this morning and graded just a few papers in, but that's all. And then occasionally when I'm doing a lab or something else, I might get a couple graded. Like the previous class, there were a few students finishing up a lab. I got a couple things graded. But usually all my grading is on Tuesday and Thursday because I just don't have any time on Monday, Wednesday. And so usually I get them graded but not put in Blackboard until generally Thursday afternoon or the weekend. Well, last week I was notified that I had been placed on a screening committee for a biology position. Well, I'm not a biology instructor, but for some reason I'm on a screening committee for a position. They have like 18 applicants, and they wanted to meet, last Monday. I said, I can't. I've got class all day long. Can I meet Tuesday afternoon? They said, well, if it's okay with Human Resources, it's okay with them. So Human Resources said, fine. So I went over there, and at Human Resources, they said, well, you didn't have to be here. You could have done it from your office. Well, I had wasted 30 minutes driving over there. I could have done it from my office because they went to online packets rather than paper packets. They used to require you to be in the room. You couldn't take anything out of the room. Now they're letting it be on the computer anywhere. So they just told me that. But they couldn't give me a password. That wasn't working. So they had to go through a whole bunch of rigmarole there. That took about 30 to 45 minutes. So I had less than 2 hours. I'd already wasted half an hour driving, and now most of my time was spent. So I started doing it online, sort of figuring out how and stuff. And the system crashed a time or two, but I got it back up. So overall, I got 3 out of 18 done. Wasted all that time, and what's more, the dean had said, oh, just look at mine and do what I did. Well, I looked at hers, but I also looked at the package. 2 of the 3 that she had done, that the group had done, were wrong. So it's a huge headache. So basically tomorrow, I'm anticipating every bit of office hours I've got tomorrow will not be spent grading papers, but we'll be doing those screenings. So don't expect to see graded papers show up until, I would say, probably Sunday, and I may not even get them done by then. I'm going to try to take some time Friday, especially if it's raining, to get a few done then, and then maybe I'll have some time Sunday afternoon. Usually Saturdays are pretty well shot. In fact, I know they're going to be pretty much shot because we're going out of town, but I'll still try to get them done when I can. But I'm going to get behind, and it may take a while for me to catch up. That's the bottom line. Okay, Megan came in. Okay. I guess y'all know the good news, bad news situation, don't you? The bad news is Tuesday's a holiday, 4th of July, there's no school. But the good news is it won't affect this class any. We get to meet both days next week. So there's the good news together with that. Silver lining. Okay. All right. Enough of that. Now, I'm pretty sure we did this slide. Whoops. This slide last time. This was the one on the loop rule. Yeah. So, in fact, we did an example with it, but I guess I didn't advance the slide any. Waiting for it to come up. Okay. So this, I'm sure we did this slide. And didn't we do the problem-solving strategy? Yeah, I'm pretty sure we did. Okay, here's where we're beginning today. I don't know why it was on a previous one. And this is RC circuits. This is 18.5, Chapter 18, direct current circuits, and 18.5 is RC circuits. Now, what does R stand for? Resistance. What does C stand for? Capacitors. Okay, so these are circuits that have both resistors and capacitors in them at the same time. So when a direct current circuit contains both capacitors and resistors, the current will vary with time. Now the reason it varies is capacitors have to charge. And when you first turn it on, it acts like, and here's Brianna. Okay? The current is slowly increasing, depending on the size of the capacitor, of course. And when they're discharging, they slowly decrease. So the current does not remain constant. Okay? When the circuit is completed, the capacitor starts to charge. The capacitor continues to charge until it reaches its maximum charge, which is Q is equal to C epsilon, where epsilon is the EMF. Once the capacitor is fully charged, the current in the circuit is zero, because no current flows once the capacitor is charged. Now, you might be asking yourself, why isn't this V here? We used to say Q is equal to C delta V. Remember that if there's no current, the voltage across the power supply doesn't have that internal resistance anymore, because with no current, the internal resistance has no line loss. So you actually go to the EMF of the battery rather than the voltage, the normal terminal voltage. And that's a little bit larger. Okay? Now, in reality, we usually ignore that. But for right now, that's what we're using. Okay? So again, the charge on the capacitor varies with time, and here's how it varies. Q, which is the charge at any time t, so this is the variable charge, is equal to capital Q, okay? I hate that it uses the same letters like this, which basically is the maximum charge. I thought they were going to show it on the slide, but they don't. So you have to look here in your book. That capital Q is your CE, C epsilon. That's what the capital Q is. That's fixed. Whatever the capacitor is and the electromotive force of your power supply, that's your capital Q. The variable Q, the charge at any time t, is going to be that capital Q times 1 minus e to the minus t over RC. So we call that denominator here, RC, the time constant. And usually they'll give that the symbol tau. Now, tau in other contexts, like maybe in Physics 201, we may have used tau for torque. Quite often we do. Not talking about torque here. This is RC. This is a time constant. I almost feel a little bit of an obligation here to show you the units are indeed correct, okay? You probably don't care, okay? I don't know. Resistance. Not really a good unit for resistance, I mean ohm, but what is a resistance? A resistance is voltage over current, right? Well, what is voltage? Voltage is energy per unit charge, okay? Current is charge per time, right? So if you did that, that would be multiplied, invert and multiply here, that would be T over Q, okay? Which is a rather strange unit, okay? Now capacitance. Let's go back to capacitance. Capacitance is charge per unit volt. So I'm beginning to wish I hadn't done that. Capacitance is charge per unit volt. Okay? So when you multiply RC together, look at what you get. The volts go out. And Q is charge. I is charge per unit time. The charges go out. And the time winds up 1 over 1 over time, which indeed is time. So that was the easier way. We didn't need to do that at all. So sure enough, that is a time in seconds. Okay? So we call that time constant tau, which is your product of your resistance times your capacitance. Okay? The time constant represents the time required for the charge to increase from 0 to 63.2% of the maximum. Where did that come from? Have you ever done much statistics? Okay? Does that, what 632 ring a bell with statistics? Isn't that generally about 1 standard deviation? Yeah, that's what it is. 1 standard deviation from away, okay? So that's what your time constant is, okay? The charge approaches the maximum value C epsilon as T approaches infinity, okay? After 1 time constant, you're up to 63.2% of that maximum value. 2 time constants are going to get you something around 96%. 3 time constants really close to 99%. I may have the percentages off a little bit there, but it's something about like that. It approaches it pretty quickly. Never ever reaches it, but it's very, very close to it. Okay? And this figure you see as in figure 1817B. They don't show the A part, but they show the B part. Okay? Now, notes on those time constants. In a circuit with a large time constant, the capacitor charges very slowly. Okay? Now, what will give you a large time constant? Either a large capacitance or a large resistor or both. Okay? Both will really make it large. Okay? The capacitor charges very quickly if there's a small time constant. Now, after T is equal to 10 tau, or 10 time constants, the capacitor is more than 99.99% charged, so we'll call it 100%. Okay? Very, very, very close to fully charged after 10 time constants. Pretty close to it after 9 and 8 too, but yeah, they're using 10. All right, what if you're discharging the capacitor in an RC circuit? In other words, you've had the circuit connected, the current started off pretty fast and then slowed until it came very close to 0 as you got closer and closer to the maximum charge. Then you turned off the circuit, and now the capacitor starts discharging. When a charged capacitor is placed in the circuit, it can be discharged. Now this could also be you fully charged it, and then you turned off the power supply. Then the Q here, without the 1 minus, is Q times e to the minus RC. And again, RC is your tau, time constant. The charge decreases exponentially. At T is equal to tau, or 1 time constant way, the charge decreases very quickly to 0.638, which is the complement of 0.632, okay? So that is the complement of that, of your Qmax. In other words, one time constant, the capacitor loses 63.2% of its initial charge, which is the same amount that it gained when you were charging. The charge has its maximum value at t is equal to 0 because it's fully charged there, and then decays to 0 exponentially as you approach infinity. Now, why is the charge going to 0? Because you've turned off the power supply, so after a while there's going to be no movement of charge at all. Okay? Does that make sense? Okay. And this, again, is the B part of the figure 1818. And unfortunately, that's all they gave you on RC circuits. Okay? I'm sure they'll give you a few problems. There are some in the text. One is timed windshield wipers. I think most newer cars have these now. You can either have them running constantly at high speed, that's what I remember in the old days, or now you can have, I think in my car there's like 3 or 4 different levels of timed wiper, like swipe, swipe, and you turn the knob. And that all depends, that's all determined by a RC circuit. Okay? Bacterial growth. Okay? It acts similar to a discharging or charging basically of a RC circuit, but it's not an RC circuit. Roadway flashers. Okay, you've seen them, haven't you? This is the orange thing, and it just blinks. And it's just running on a battery. It just has a resistor and a capacitor in the system, and it blinks. So basically what it's doing is charging up to a level, coming on, and then shutting down, charging back to that level, coming on, and shutting out. So you can read about it here. There is a quick quiz here, and this is referring to figure 1820. Do any of you have books? I don't think so. Oh, you do. Okay. Let me see if I can draw this circuit. And I'll try to draw it down here because I've got a little more room. Okay. Here is the circuit. We're going to start down here with a battery, a 6-volt battery. Plus side, minus side. Okay? We're going to come up here to a switch. Okay? That's just a switch. It's on page 604. It's Quick Quiz 18.9. Okay? And then you come over here. Whoa, goodness, I can't draw a straight line at all, can I? Try to do better on that. Coming across here, and then you have a branch coming down here and a 1 farad capacitor. Now, what does that sort of look similar to? It looks a lot like a battery, but a battery has a long and a short line. A capacitor has 2 equal length lines parallel to each other. That's the symbol for capacitor. That, by the way, is the switch. This capacitor is a 1 farad capacitor. Okay? That is a huge capacitor. Most capacitors are measured in micro or pico or nanofarads. Okay? That's a huge capacitor. And in that same branch, you have a resistor, and that's a 1 ohm resistor. That's a terribly tiny resistor, though you can have things smaller. Now down here in this leg, let me get my minus sign elsewhere. Okay, minus here. Down here you have another 1 ohm resistor. Okay? And then over here you have a 2 ohm resistor. And that's all you got in that branch. Man. Okay. Okay. Initially, your switch is open just like you see it here. And then you close it. Close that resistor. Close the switch. All right. Now, initially, you start charging the capacitor. But at the very beginning, the capacitor is like, it's just part of the wire. Okay? It starts charging immediately. Okay? And since this is only a 1 ohm resistor here, the capacitor doesn't have any resistance per se. Oh, I forgot to plug this one. This is 1 ohm at the bottom too, I'm pretty sure. Okay. Then the current comes here, and it sees 2 ohms this way and 1 ohm that way. Right? Which way is the current going to go? It's not the direction. Which leg? The 2 ohm or the 1 ohm resistor? Oh, the one. Is that the one? No. Oh, okay. Huh? No, it's not good because there's more resistance there than there is here. Okay. So the current is going to initially start going there, but after a while, this capacitor starts charging. Okay, as it starts charging, then less current flows through here, so this looks a little more attractive over here. So now some current starts going over there. Of course, all the current has to go through this 1 ohm going back in. So, sort of a strange looking circuit here. So the switch is closed in 1820, this figure here. After a long time compared with the time constant in the circuit, okay, what will the current in the 2 ohm resistor? What will be the current in the 2 ohm resistor? After a long time, several time constants, this is fully charged. That's now an open circuit. No more current is flowing because that's fully charged. So now all this battery sees is 3 ohms, because these are in series. 6-volt battery, how much current? Six-volt battery, 3 ohm resistance, how much current? Huh? Okay, what's Ohm's law? What is Ohm's law? That was basically a chapter ago. Wasn't it? Yeah. What is Ohm's law? Y'all did a lab on it last time. You've done your test on it, I bet. What is Ohm's law?
Talking about the equation?
Yeah.
The R equals V over I?
That's one form. Right now we're looking for I, so how would you do that in terms of I?
V equals I.
Second? V is equal to I is another form. That gives you V. What do you do to get I? No. V can't be IR and I be VR at the same time. V is equal to IR is correct. That's the basic form of Ohm's law. So how do you solve that for current? Second? How to solve that? You're trying to find the current. Okay. Gave it to me correctly. V is equal to IR. Let's solve that for current. Solve it for current. What would you have to do? Look at the board. Yes, V over what? Okay. That's solving for R. I want to solve for I. Look at the equation. If we want to solve this, isolate the I. What do we do? V over R? V over R, of course. V over R. Divide both sides by R. The R's go out here, and I is equal to, if you want to call it, delta V over R. And what did I say the resistance was? When this is closed, in other words, this is fully charged, fully charged, no more current is flowing through this leg, what is that? All the current has to go this way. So what is the effective resistance of two resistors in series? 1 and 2 ohm resistors. Say again? Okay. What is the equivalent resistance of two resistors in series?
Is it a number?
Well, no, it's a concept. What do you do to the resistors if they're in series with each other?
Oh,
Add them. And 2 plus 1 is 3. So there's your resistance. Your voltage is 6 volts. 6 divided by 3 is 2 amps. Whew. Okay. So this is 2 amps. That answers the first question. No. Here's what it was. The switch is closed after a long time compared with the time constant of the circuit. In other words, for the capacitor to get fully charged, so there's no more current in that middle leg. Then what will be the current in the 2 ohm resistor? Okay? Well, the 2 ohm resistor will be the only current going, and that will be the one. Where did it go? Oh, it went. There it is, okay. And this gets fully charged after several time constants, it's fully charged, then this, no more current flows through here, so all the current goes around this way, so the current through here is the same as the current in the whole system, and that system has a voltage of 6 volts, total resistance of 3 ohms, so that would be 2 amps. 2 amps. The options here were A, 4 amps, B, 3 amps, C, 2 amps, D, 1 amp, E, more information is needed. What did y'all say? 2, which was C. Let's see if they got it right. Topic 18. This is number 9, C. Perfect. Okay. That, by the way, is the last quick quiz in the chapter. All right. Any other questions on capacitors? RC circuits. Now they're moved into, and there's several examples here, like I was going to say, I mentioned roadway flashers, charging a capacitor in an RC circuit. There's an example there. And there's discharging the capacitor RC circuit. There's an example there. Then 18.6 is household circuits. Okay? Your utility company, they often call them power companies, but really should be the energy company, distributes electrical power, and again, that should be energy, to, if you're saying power, call it the power company, to individual houses with a pair of wires. Okay, sure. Okay. Electrical devices in the house are connected in parallel with those wires. The potential difference between the wires is 120 volts. Now, I have a problem with this. Utility company distributes that to individual houses at way more than 120 volts. I would say most of the time it's more like 360 volts. Okay? And then they split off the 220s to go to the big appliances and 240 to go to the big appliances and 120 to go to the smaller ones, which is most of your plugs. So the electrical meter measures the power. Right, okay. That's okay. I really do not like the way they're saying this. Okay. The electrical meter does not measure the power in watts. It measures energy consumed in watt hours or kilowatt hours. Okay. I don't think any meter measures watts, but maybe they have something. I don't know. What they're saying is you're supplying 120 volts to the system, and then you have a circuit breaker here. Usually it's closed. Okay. The top half of the circuit breaker I do not like the way this is drawn either. Okay? This is showing that the neutral is connected here, and if that were the case, you wouldn't go anything down here. Okay, but that needs to be a little bit separated there. So here's your various devices in parallel. Okay? And then this goes to ground, which is your neutral line. As you operate any one or more of these, then more and more current is going to go through here. The more you operate, the more in parallel. And if the current that's going through all these combined exceeds what the circuit breaker is rated for, it's going to spring. And then your circuit breaker goes and you lose power to all those that are on the circuit. Because the circuit breaker is in series with them, but they're in parallel with each other. Okay. Electrical devices in the house are connected in parallel. Yeah. The potential difference between the wires is about 120 volts. Yeah, we got all that. Now, a meter and a circuit breaker are connected in series with the wire entering the house. The wires in the circuit breakers are selected to meet the demands of the current circuit. If the current exceeds the rating of the circuit breaker, that's what I was just saying, the breaker acts as a switch and opens the circuit. Household circuits actually use alternating current and voltage, not direct current. So things are a little bit different there, but overall you can treat them pretty much the same. Okay? Here are the details of your circuit breaker. Okay? The current passes through a bimetallic strip. Okay? So here you've got your wire coming in. Here's your contact points. As long as you have the circuit breaker in the closed position, that makes good contact here. You have a spring here that is always pulling down on this, but this is keeping it off of it. Okay? Now, your current goes through here and goes through the bimetallic strip and out. Now, why bimetallic strip? Any ideas? Huh? Cheap? No, you need it to do a function. And here's what the function is. Now they show you this is copper, or it looks like it's copper. Copper is a great conductor. I think they got it backwards, okay? This over here is not copper. I'm going to guess aluminum, it could be iron, it could be anything other than copper, okay? Now, I think they got this backwards. I think the other one needs to be on the outside and the copper on the inside. Because when the current flows through here, when the current flows through here, the copper is going to conduct pretty well, but this doesn't conduct as well. This is going to heat up. That's why I think they got these backwards. And since it's going to heat up, it's going to bend this way. And when it bends this way, then it hits this V. Now the spring can pull downward, and that pulls these apart, and your circuit breaker opens. Okay? And you reset it by flipping the switch all the way off, moving the bimetallic strip back where it needs to be, and then resetting it. Now, we have one circuit in our house, not really in the house, that the circuit breaker trips every time it rains. Not every time, but a lot of times when it rains. It usually don't trip unless it's raining. The reason for that is an outside plug. And obviously the rainwater is into the thing and provides a completed circuit, and too much current goes through that, and then this heats up, trips, and it breaks. Then we usually wait until after the rain's over, it dries out, we do it, it works fine. It's our outside lighting. So just about every time it rains, that goes out, our lighting goes out, and then we have to wait until it dries out and turn it back on again. So we know that works, and we're thankful that it works. Because otherwise, it could get so, if too much current goes through there, it could heat up enough to burn this, start a fire in the system. All right, now we also have 240 volt connections. And why? Okay. They don't have this section in the new edition of the book, but let's just go and cover it since it's here. Your 240 volt connection, what you do with that, you have heavy duty appliances, and what they mean by that are appliances that require a lot of current. Okay? So what you do, and what would those be? Name some that would require a lot of current. Think of things that have a lot of heat associated with them. Second? Microwave, I guess some might, but most of them don't. They're usually 120. Second?
A heater. A space heater?
Okay.
A space heater?
Space heaters, most of them, if they plug into a regular socket, no.
So is it plugged in?
Anything that plugs into that is 120.
Oh.
A stove, absolutely. If you have an electric range or oven, they are going to have these plugs. Okay? Lots of heat, so it has a lot of current, so they up the voltage. There's another one. Just about all houses have.
What is it?
A dryer, producing a lot of heat. They have that plug. Your washer, regular plug like that. Now, you don't see it, but most of the time if you have central air conditioning, that compressor is going to be doing a lot of heat, so that's going to be on a 240. Most of the time that's hardwired in, they don't have a plug for it. Some of the window units, before my parents got air conditioning in their home, my grandmother, when she got ill and came and had to live with us and was confined to her room, and the room would get really hot, we put in a window unit in there. And at one point we had a 120 that just couldn't handle it. So a friend of ours found the 240 for us, and then he had to wire it for the 240. Because some air conditioners are 240 over or 120. Typically, the plug will look like this. A plug here and two angle plugs there. Now, your stove and your dryer nowadays have slightly different. One of these has a little wing on it. I don't see any of these do, but it has a little key in it, so you can't use the wrong plug in the wrong nut. So I don't know the reason for that. I'm guessing the stove needs actually a heavier duty wire than the dryer does, is what my guess is. Okay, so what they do, they provide another wire at 120 volts too, but this time they put it below the ground potential. So you have a plus 120 here, a minus 120 there. This one's going to ground, which is neutral. So you have a potential difference here of 240 volts. Okay? And that's typically how that works. Now, electrical safety. This is 18.7. Electric shock can result in fatal burns. I don't usually think of the burn as being the part that's fatal, okay? But I guess it could be. But electric shock can cause the muscles of vital organs, such as the heart, to malfunction. And basically, that's what kills you, okay? If you get shot, by the way, time out here. How would you classify us as beings? What kind of machines would you say we are? We're not quite robots, no, but we are electrical machines. The reason you can see, the reason you can hear, the reason your heart beats, the reason everything happens, you think, oh, my head itches, number one, that's a signal, and then I'm going to move my hand to my head and scratch it. That's a signal. All these are electrical signals that go very, very rapidly. The electrical signals in our body are basically the potential difference. Remember when we did the potential difference lab? And a few of those metals were very small potential differences. I think a few of them were like 0.1 or 0.2, right? Volts, even 0.01 or 0.02 volts, right? Very small. Guess what? In our system, the potential difference is a fraction of a millivolt. Very low potential. It's the difference of the electronegativities of a sodium ion and a potassium ion. And they are really close to each other. That's what sends the signals through your body, basically at almost the speed of light. Not quite, but very close. That's why you can react immediately. I mean, I don't know if you realize something. Something can come flying at your eyeball at such a high rate of speed or from such an angle, you don't have time to think about it. Your eye senses that and closes the lid like that. I actually had a friend from Nebraska. From Nebraska, who had worn glasses all of his life. I mean, close to 20 years. Okay, big old thick glasses, but he had that surgery that they do that corrects. It's a laser type surgery, and it corrects something in the eyeball, and he didn't need glasses anymore. But he had been his whole life with glasses on. He had lost the reflex to blink when something comes at him. And he kept getting, for the first few weeks, stuff in his eye until we learned how to, and it was a reflex. It's totally a reflex. You don't have time to think about it if something comes real quickly. You don't realize your eye closed. Your system is that fast, okay? So if you're operating, your whole body, your heart and everything else, your muscles, everything are operating on a potential difference of a few millivolts, and maybe even a fraction of a millivolt, and then you connect with 120 volts, guess what? You fry your system, basically, okay? And if you do, that may be the fatal burns they're talking about, but basically you upset your whole system, and if your heart stops because of that, you're dead, unless it starts back really quickly. What was the old means of execution in Alabama? The electric chair. That's how they killed people, okay, when they were executing. Not particularly great. I mean, there was pain involved and stuff like that. That's why they went to lethal injections, and now they write that that's painful too. I don't know. Now, the degree of damage depends on the magnitude of the current. And believe it or not, it's usually the current that causes the burns, not the voltage. The length of time that it acts, the longer that current is doing, the more things it's frying. And the part of the body through which it passes. If it passes through a leg muscle, yeah, you'll get over that. You may have a burn there for a while, but you'll get over it. If it passes through your heart, you could be going in an instant, okay? Just like the old electric chair. What did they call it? Was it the Yellow Mama or something like that? They had a nickname for it. It was pretty gross that they made fun of that. Okay. Now, let's look at the effects of various currents. Okay. 5 milliamps or less. That causes that sensation of shock, generally little or no damage. Remember when we talked about in the first, second chapter, something like that, of static electricity? That can be in this range. You feel it, you jump at it, but the thing is it doesn't cause any damage, or very little if any. If you're up to 10 milliamps, now that's still pretty small. Your hand muscles contract and may be unable to let go of a live wire. Now, actually, when I was in high school, probably, it was either junior high or high school, either 8th, 9th, or 10th grade, had to have been one of those. Okay? I'm thinking it was probably 10th grade. We used to have a fair come to town every year, okay? And they had set up and all the rides, and they had wires running everywhere and all over the place, and you weren't supposed to go back in the thing. You were supposed to stay out in the walking area. So these guys, there were several of them were in my older brother's class, that was 2 years ahead of me, and one of them was in the class just ahead of me. He was on the basketball team, and one of the other guys was on the basketball team. Pretty good players, too. And then there were some other friends of theirs who weren't on the basketball team. But they were walking along, and Phil Chalker went to duck to go under something and reached up for some reason, and he grabbed, and the fair people should never have had this there, he grabbed the live wire. And when he did, just like it says here, his hand muscle contracted, he was about to electrocute himself. I think it had rained, so there was good conduction and stuff. The grass was wet, and he was, and Pat Thompson, who was a little twerp in my mind, but he really thought quickly here. He picked up a piece of wood or a baseball bat, why there was something like that hanging around, I don't know, and basically knocked Phil's arm off the wire, because Phil couldn't let go because his hands contracted and he was there basically electrocuted. And Pat knocked it. He couldn't have pulled it down because he would have been part of the circuit. So he picked up the baseball bat that was not a conductor, knocked his hand. He broke his arm, but that was okay. He didn't electrocute him, okay? Electrocute himself. And that actually did happen. The hand muscles contracted and he was about to go, okay? Now, if you have up to 100 milliamps, and again, that's 1/10 of an amp. Not a lot of current. If that passes through the body for just a few seconds, you could be dead. Okay? You know, could be fatal. So again, it's how much, how long, and where it passes through. Okay? If that passes through the whole body, too many things are going to get out of whack really quickly. Okay? Here are some things they do with power equipment to try to build safety into the system. Most electrical equipment manufacturers use electrical cords that have a third wire called a case ground. Okay? I've just heard it called the ground, but it's called the case ground. What it does is tries to prevent shocks. Okay? You see, if you're here and you don't have that case ground, you only got the two-prong circuit here, and our house was built in the 1930s, between 1929 and 1930. It was being built in that time frame. Most of the original circuits in the house were two-prong, not three-prong. Now, we've had several added, and as other improvements have been made in the house, other people had them added. So a lot of them are now three-prong, but not all. There's still a few two-prongs in there. Okay, and in the old equipment before this, then you have high voltage coming in one wire, and you have the ground or neutral going to ground of the other wire. 120 volts across there, because that's the standard circuit there. Now notice all these are three-prong plugs, not like this, okay? Two-prong. And you're operating the equipment. Here it's a drill, and it happens to something shorts out. Now, actually, one thing that could happen, you're drilling into a wall or something, you happen to hit a wire, and now the drill has full charge coming through it. If you don't have that other ground, you become a better path to ground than that is. Much shorter path, and if that goes through your heart, you could be dead. If it just goes down like this, it could freeze you. So, what happens with a case ground, if that case does pick up any charge, it goes through the green line here, and it doesn't go through you, it goes that way, it goes directly to ground. Okay? The other thing they show here, and it's a great exaggeration, but if you look at these plugs here, I'm pretty sure you'll see it in every one of them. You see that one side of the plug to the right is, these are flipped over because these have the grounds on the bottom and this has it on the top. So this would be the one on the left, and that's what I see. The one that is a longer slot, and this is a shorter slot. The shorter slot is the hot wire, the longer slot is the ground, and that's connected to also the neutral three-prong there, and that takes it away from you to ground. Okay? So that's one. It helps prevent shock to the operator. Now, that may or may not be enough. They also have, and generally these occur in kitchens, in bathrooms, and in external circuits, like the one I was talking about in our outside. It has a ground fault interrupt in it. I have a younger brother who works for an electric company, and he hates GFIs, and he shorts them every time he can. I mean, he doesn't like them in his house. I think it's a very dangerous thing to do. These are special power outlets, and what they will have, they always have a little button on it that you can reset. And like I said, they're usually in areas where you have water, like bathrooms and kitchens and external areas. And these special power outlets are used in hazardous areas such as that, designed to protect people from electrical shock. Well, the two prongs being different lengths, that is a small protection. The third prong is a protection, but this gives you one other level. It senses currents of about 5 milliamps or greater leaking to ground, and if it senses that, it shuts off the current above that level. Okay? I don't know if you remember the old mystery shows on television or movies and stuff. One way they always had of people knocking off somebody else, say a wife or a husband, they would drop a hairdryer into the tub while they're taking a bath, and that would electrocute because the water is a great conductor, and the whole thing's in there, so the third prong doesn't help you. You're fried, right? Or boiled, or what? No, I'm sorry. Okay, but with a ground fault interrupt, as soon as that 5 milliamps or greater it senses it, it shuts down the whole circuit. So that's the advantage of having that. Okay, it's better than just having a case ground. It shuts the whole thing off, and that's why that reset button is there, so that if it does shut it off, once you get the situation remedied, you can start it back again. All right, then 18.8 is electrical signals in neurons. This is talking about what I was saying earlier. We are electrical devices, machines. Specialized cells in the body, called neurons, form a complex network that receives, processes, and transmits information from one part of the body to another. There's 3 classes of neurons. Those that sense, for instance, your sense of feel, your sense of sight, your sense of hearing, sense of smell, those are all your sensory neurons. Receive stimuli from sensory organs that monitor the external and internal environment of the body. Then you have the motor neurons. They're the ones that if you sense by vision that particle coming toward your eye, the motor neuron carries a message that controls the muscle cells and says muscle contract to pull your eyelid down. Those are the motor neurons. And then they have something else called the interneurons. Okay? These transmit the information from one neuron to another. Okay? So if you need something connecting a motor to a sensory or sensory motor to motor or something else, the interneurons transmit the information from one neuron to another. And here's basically how they look. This is figure 1825 in your text. And I don't know if you need to know all this or not, but here we have the synapses. Those are the things that connect to these dendrites, which are the things that are sensing things. Okay, I'm sorry. This is sending the other way. Okay? These are the nerve endings which are sensing things. They go through these cells that are called axons, I guess that's how you pronounce it, into the main cell body. There's the nucleus of this cell. The synapses are here, which connect to them, and they send signals back and forth from other neurons, as your synapses. And the dendrites are things out there that other things can connect to. Okay? Read the text to get a little bit better description than what I'm giving. Okay? And that's it. So you have to read the text to get it. What's that? That was it for this chapter. Okay? That's chapter 18. Okay? Say that again. Well, not quite. We're close, but not quite. Let me just go over this. There's a summary at the end of the chapter. Oh, there's another page and a half of text that you have here that the slides didn't do much on. I would definitely. Okay. Y'all have books?
Yes,
Yeah, right. Okay. All right. All right. Now, after the chapter's over, there's a summary. It goes through each section, 18.1, 2, 3, 4, 5. That pretty much closes. They don't do much on these last 3. Okay? Then you have a bunch of conceptual questions, not too many. Those odd numbers have the answers in the back. Then the problems. That's the place, I think, of most important place to study. And any of the odd numbers have their answers in the back. So from 18.1, you got 1 and 3. From 18.2 and 3, these are together. Those are 5 through 17, so quite a few of those. Then Kirchhoff's rules and complex DC circuits, that's at 18.4. Those are problems 19 through 31. Quite a few of those. Your RC circuits, not as many. Odds 33 through 37. Household circuits, odds 39 or 41. And conduction and electrical signals by neurons, that's 43 and 45. Then they have some additional problems that combine several features together, and those would be any of the odds 47 through 67. Okay? Now, I guess this probably would be a good place. It's not quite lab time yet, but it's close enough for me to set it up. I think by the time I get it set up, it will be lab time. So, all right, she's really a good salesman tonight, isn't she? Okay. So and we got started late, so that really should have been our break time then. Okay. What we're doing here is electric circuits. It's listed as experiment 20. It's actually your lab, what, 5? Okay, lab 5. An electric circuit is a path for conducting path for an electric current. The circuit is the path, the current is the flow of charge. Okay? They have some of the circuit elements listed here. The battery is always a series of short lines, long lines, short lines, long lines. You can have as few as 1, or you could have as many as, say, 3 or 4, 5, 6, 7, whatever you have. Usually each one represents a cell in the battery. For instance, your car batteries have 6 cells, 2 volts each, so it turns out to be a 12-volt battery. So different ones will have different symbols there. This is the ground, which we use mostly for AC circuitry, so don't worry about it here. Your bulb is here. Now, if you'll notice, a resistor is down here. It's just a squiggly line. What makes a bulb is a resistor with a circle around it, meaning it's a bulb. Okay? I'll put a bulb in your device there. We're not going to deal anything with variable resistance, but that's how they represent it. Now, they do have symbols in here about switches being open and closed. We're not going to be opening and closing switches. Okay? Now, this is not important, but if you ever are doing serious wiring diagrams, if you have 2 wires that you have to get 2 different places, but they cross, but they don't really connect, then you make a little bump in it showing it just goes over the wire. If they are crossing but connecting there, then you just have a dot there indicating they do actually have a connection. All right, now the procedure, it says 1 flashlight battery, 1 flashlight bulb, and 1 piece of centimeter piece of hookup wire. Don't worry about that part. What I want you to do for the first part, well, actually there's actually a part before the first part. Okay, let me see if they reference that here. No, okay. The first part is going to be drawn in this rectangle here with the dotted lines around it. And rather than messing around with a single bulb, don't worry about that. Basically what I say is draw number 1 up here. You can even leave off the switch. Just make a connection there. Notice the battery over here, a long line, short line, okay, and just a light bulb there. Basically going to be what you have on your circuit right up here. Okay? That's number 1. Just draw number 1 up there, and you can leave off the switch. Or close the switch, either one you want to do it. Just have a complete circuit there. Yeah, close the switch, or just leave the switch out completely, just put the line straight across. Either way, I mean, yeah. I just want a circuit there. All that's in the circuit is a battery and a bulb. That's all. Okay? And that's what they were talking about in number 1, a battery, a bulb, and a wire. And that's all you got, right? We have 2 wires, but it's okay. Now, the way you drew your battery, if you did it the same way as that other one, yeah, very good, okay? The way you drew the battery, now this is the last line on page 179 under number 1. It says on page 180, make a sketch of your circuit you just did using the symbols given in right above. You did it correctly. Draw an arrow to show the conventional current, and draw another arrow to show the flow of the electron current, and then identify each arrow. Which one is conventional and which one's electron? What's the difference between the two?
One's going towards the battery.
Okay. They're both going away and toward the battery, but it's just which direction. And what is it? Okay, and which is which? Well, wait. When you did this, if this is the upper part and that's the lower part, that's the same circuit. If you're doing this, like on either side of the wire, that would be okay. Or this, one's going this way and one's going this way. What's the difference between the conventional circuit current and the electron current? Say that again. Okay. The key here, now when you drew your battery, if you look at that first page, on the one you copied didn't have it, but look back on the first page when they drew the battery. They put a plus and a minus. Where does the plus go? Okay. The battery is made of, what distinguishes a battery, say, from a capacitor? What about the lines? Short and long. And which one's the positive, which one's the negative?
The plus is by the long.
Yes, the plus is by the long and the minus by the short. So you can go on and put that on yours.
So electrical is
the electron.
It was the minus.
Okay, it's going from the minus to the plus because electrons are negatively charged, so they leave the minus and go toward the plus, whereas the conventional, they go the opposite, so from the plus to the minus.
An arrow going this way?
Yeah, and then label that, and an arrow going that way and label it. Exactly. Okay? What the difference is, the conventional circuit is the direction a positive charge would flow if you had positive charges. The electron current is which way the electrons flow, which of course are going in the opposite way. A positive charge would leave the positive electrode and go toward the negative, right? And an electron, which being negative, would leave the negative and go toward the positive. Okay, so you've done the first one. Number 2 is note the construction of the flashlight bulb. That's what here, that actually looks like it's figure 20.2, that bulb that you see on that first page, or inside, same page you were just drawing on. See the flashlight bulb? Okay. Now what does it say? Note the construction of the flashlight bulb. That is an incomplete diagram of a bulb. Complete this diagram by drawing wires that connect the filament to the contact points in such a way that there is a complete circuit for the current to follow. Now I'm going to give you a little hint on that. This is a reasonable facsimile. Okay. If you'll notice here, this is a bulb. It's not a flashlight bulb, but it could be. And you notice in there, there's 2 little poles. with a filament in between. That's what the light is. Now, look at where these wires are headed. One is on that tip down there going out, and one is on the side here going out. And that's because inside there, one of these prongs is connected to this, and one's to that. Notice what's in between? Black plastic. That's an insulator. If that weren't there, it would short out. The current would just go through the wires and not ever go through the bulb. So evidently, in your bulb, one side has to go to the casing, and one has to go to the tip of the bulb. So that's all you have to do. Yeah, a wire. Just draw a little wire to connect one of those to the casing. You have a rigid rib casing. This has a flat one, and one to that tip of the end. It doesn't matter. Yeah. No, wait. You can see your wire. Okay, yeah, but we talked about these. See, these aren't connected to anything. What do they have to do? See, you have to use imagination. What's inside here?
So break it down?
Huh?
Break it down?
Okay. This, to be connected to one of those, not. You connected it to here. Remember, see this? The outside casing. That's this. If you think about light bulbs, that it's a metal part that has the grooves in it, right? That's part of the circuit.
So we could just write our arrows like this connected,
Okay. You went from the black part, which is your plastic, which is your conductor. That's
oh, that's the black part, right?
Yeah.
Also,
That one goes to there. There. Yeah, okay. Yeah, you don't have to go to outside. That's fine. Yeah. And that one goes to, and actually, this one ends here, that one ends there, and then in your socket, that's where it connects to the other. They didn't have a socket for this one, so you wired this one in.
So I need the wrist?
You don't need the tail outside because you don't see a wire coming out of here.
Okay, so just leave it inside.
Yeah, leave it inside. Stop at the inside. Okay. Now, that's one, that's two. Now, I've got this circuit wired right here. Okay? It says, wire the circuit shown in figure 20.3. That's these down here. I've got the first one done for you. So come take a look at it. These are the ones at the bottom. You're reading number 3 here. Okay? Think of this as the plus side of your battery. It's the high side, so that's the red line coming in here. It goes to one side, connects to the bulb, and then comes out here. Now you can't see this, but you see this one's connected to here, then this insulation, then this one's connected to there. So that's why it goes in here and comes out there, and that's why I did it the way I did here. Okay, so this is connected here, goes through the bulb. Actually, you can follow this better this way, and it comes out here. Yeah, that's why it's connected up and down. Okay? Now, what I'm going to do next is turn on my thing. It's at 0. Now, what I want you to do is turn that on, and now I don't want you to burn out my bulb, so don't get a bright light. I don't want that. I want it just so it's easily seen. Not really faint, but easily seen. So you twist the knob until you get, do it slowly and look at the bulb while you're doing it. Okay, that's pretty good, don't you think? Okay. Yeah. So that, now, if you're happy with that, that's what you call your standard brightness. Standard brightness. That's what you're going to call it from here on. That brightness right there. Okay?
So this circuit one is simple circuit?
Okay, so number one, you can put, and you're turning to the right page, on page 183, you can put the simple circuit, you can put what you call that standard brightness, and if you want to, you can identify it as 3.5 volts. If you're happy, that's standard brightness. Is that bright enough for you? Okay. Now, I want to move over here just so I can record better. That's standard brightness. Now, what you do from here on out, okay, you can go and turn that off now. Okay. Now, what you do is set up each of the other circuits. First, do number 2. And there's 2 observations I want you to make on every circuit. You see over here on number 2, it says observations. Here are the 2 observations you make. When you set the, here's the one other thing. Notice here, number 1, that had a single big bar, little bar, right? And you identified that as 3.5 volts. So that's what that stands for. Now this one, they put them further apart, but it's still a big bar, little bar. So you're going to use the same voltage you had here, right? So you're going to set that up. But first set it up and put these 2 in, what do you call that when they're connected like that? Series. Those are in series. Okay, now remember when you're doing this, and you have your other bulb, you see that? Okay, remember, you unplug this, and remember this one has to be, yes, I'll show you on this one. That has to be here because these have to be on the same strip. See?
So it doesn't matter for the power.
No, well, let's see, there it is. There you go. And then you plug this in. You're absolutely right. That's in series. See it? Okay. Now set it up with the same voltage that you had before.
0.35?
Yeah. Okay.
Is that 3.6?
Huh?
Or is
Okay.
that
And you may not be able to see it. You see anything? Oh yeah. Now here are your 2 observations. First is that dimmer than the standard. Is it standard or is it brighter? Okay. So it'll be one of those 3 answers, except maybe one of these will have not on at all, which could be dimmer than the standard. Okay? Okay? The second observation is what happens to one bulb when you take the other one out. It goes out. Okay. Okay, so those are the 2 observations you're going to make with everything that has. Now, of course, if it only has one bulb, you can't remove one bulb. But when it has 2 bulbs, what is their observation when you remove one? So on every one, you're going to put a brightness thing. Dimmer, standard, or brighter. One of those 3, or it may be off. That would be okay too.
Okay, what is it when you do 2 batteries?
What's that? Okay, that means, now, and that's a very good question. Normally that would mean put twice the voltage. I don't want you to do that. I want you to increase the voltage and tell me when you can tell a difference, whether it's brighter, dimmer, or standard. Okay? Okay, but you haven't set up the circuit, have you?
Is it the same? No, it's one.
One bulb.
But you increase the voltage.
Yeah. Get it to the 3.5 and start increasing voltage and see what happens. And increase it slowly. Don't. What's happening to the light? Brighter. Okay, that's the only observation you can make because you're not removing the bulb, right? Okay.
So what would it call this
What's that?
standard brightness? Would you say brighter than standard brightness?
Yeah, brighter. That's brighter than standard or just brighter. That's all you really have to do. Okay, you think you can proceed with the rest of them?
You have to write the voltage first.
What's that?
You have to write the voltage. The voltage.
What about it? No, you don't have to write it. Just that it's when you increase the voltage, it got brighter. Now, if you have any other questions, ask. I'm going to pause this for now. Okay, what's the question?
Because it asks for them to be parallel.
Parallel.
How are they going to do the same circuit if this one's not?
Okay, now that would be serious. So it's okay if you do it here, that's fine. Okay, but what you have to do now is look at the parallel. Okay, you see on the upside, which is the red, these two bulbs are both connected on the upside. See it? Like that. Right? And on the downside, they're connected like that. And then you put that out there. Right? What's your battery status? Okay. What do you think? Standard brightness. I agree.
So we're removing these.
Now remove one of them. Doesn't matter which one. Don't disconnect any wires. And it does stay on. It certainly does. Okay.
Are they up under here?
What?
The other bulbs.
What do you need another
So
bulb?
2 bulbs are parallel and 2 another batteries.
Yes. In other words, twice the voltage. But you don't have to do twice, just increase the voltage until you see what's happening.
I really want this on.
Okay, what's the question?
Circuit 7. How do I tell which arrow
Oh,
has
okay.
capacity?
Okay. Now you don't have to set up correctly, and I'm glad. Okay. This one I didn't really want you to set up, but it's okay. Because you see this wire is going nowhere. This one is this strip, nothing's in that strip. And this one's going nowhere.
So I need to switch them.
No. Here's what it would be. And it's just a single, so it's 3.5. Let me see the diagram again.
That's all.
Okay. Right. Okay. Now, notice on that, I'm going to put it on the upper side just like that did. So let's say it goes into this strip here, and this will be connected to this strip here. Okay, that's what is going to happen. See, and this is just wire here. In fact, you could just do it like this. That's the best way. You see, this is going,
So the right way would be the same thing going out through.
yeah, you see, this is going here or through the bulb. So I'm going to do it real quickly and tell me what happens to the bulb.
So,
Now, show on your diagram, you can either use this diagram or draw it on the other one. So number one, the bulb goes out. That's what you need to flip. That's an observation. Okay? And you want to draw that or use the other drawing that you had already?
once down on the 7.
Like that. Whichever you want to. You can draw it in there or you can use number 7 over there. I don't care. And again, you don't need a switch in. I'm going to go and turn this off if you're okay. Why did the bulb go out and connected this wire there? I've turned off the fuse, so when I put it there, why did the bulb go out? Or what? You're absolutely right. This has basically very little resistance. That has resistance. And guess what current does? Acts like students, follows the path of least resistance, right? I didn't say that. Okay. So the current is going to go this way rather than going through there, because that's too much work to go through there. Right? So then draw on your thing where the current goes.
Did you draw it like that?
So it
Yeah,
would
yeah.
go over.
It goes through the wire rather than going through the bulb.
So is that okay?
Yeah.
That's fine.
That's fine.
Or just on the outside.
Yeah, the point is it goes through here rather than going through there.
So did you try to, he said you can use this or the
Or just, I do myself.
just make sure you see it and turn the page back.
Okay, you just say turn the page back.
So you said I could draw it like it's going over.
Yeah.
And you said this is the least. So the area that has to
And then basically number 8 really looks just like number 6. It's just got switches in different places, but we're not using switches. It's just like number 6. So you can, I'm sorry, got 6.
So they're both just going to be on top of each other. Or does it matter if it's on the same one?
You gotta have it where the pin is. So you see, this isn't gonna work because there's nothing connected to that one. And this is not connected to anything. Yeah. And this isn't connected to anything. Okay. Is that what the other one was? Is that how you had it set up?
Mm-hmm.
Oh, okay. And then this is twice the voltage. Okay, but you don't have to do twice. Just do a little bit more and see what happens. Brighter, okay. Is that what you got for 6 also?
Yes.
Okay. And then what happens if you move the bulb? The other stays on.
Stays. Okay, time to answer questions. Yeah. Do we have to do this part?
Huh?
We're gonna do that part, do we?
No.
Okay, thank you. So we can answer questions now.
Now you answer the
And then
question.
we do.
And
What part did we do?
Okay, we'll.
you have to answer these questions, starting on the previous thing, right here, no, up here. Okay, start there. Oh, which part you didn't have to do? Yeah, you don't have to do that. Yeah. So start answering those questions based on what you put in your table. I don't think I said.
Um,
Number 2 or number 3?
I'll circuit two.
Circuit 2. Oh, let's turn this off. Okay, circuit 2. Let me see circuit 2.
The two
So I can
bulbs
see.
in the series.
Yeah, just flip over that page you were just doing. Hold that. Yeah. There's circuit 2. Oh, yeah. Got that. Okay. Why do you think it was different?
They're on the same
Okay. What do you call it?
series.
They're in series, which means the same. Okay, you got the same voltage here you did for Sandy, right? Same voltage. You got twice the resistance, so that basically halves your current. Okay.
Okay.
So if you got half the current, it's not required.
So I mean, you just need,
The ones that had normal brightness, standard brightness, exactly. Now, oh, and let me point this out to you too. Notice here on number 2, 3, 4, and 5, what you notice about all those? Explain. So the first part, which circuits, you'll do something like this, just list number the circuits that were dimmer than normal, and then explain. And that's what you were just asking me, right? Which circuits were brighter than normal? Explain. Which circuits did removing one bulb make the other go out? Explain. Why did removing one bulb not affect the other? Explain. So those 4, you list the circuits, that's answers the first part, and then explain. You gotta have the second.
It made it go out because the current was greater.
Where?
Yeah, the current, no, the current was
Okay.
least.
Okay, right, yeah. That was the one bulb. These 2 questions are asking about when you had 2 bulbs and you moved one and the other went out, or you moved one and it didn't affect the other. So those are only your 2 bulbs. That's the one bulb.
So it went out because they were both together in the same current, so we moved one.
Okay, I think you just said it. If they're in series, they're in the same circuit, removing one opens the circuit, right? Now that's another thing I'm glad you asked that. Okay, in parallel, notice when you remove one, you still have another path to take. That's why the second one doesn't go out. But if these were in series with each other, like that, if you don't like that, this one, then, yeah, because you've broken the circuit. Okay, now, how about that one that did this? Remember the one you were talking about, number 7? Why did that circuit go out? Did you create an open circuit there?
For number 7?
Yeah, number 7. That has a special name. It's not an open circuit,
It's a closed circuit.
not closed. These are all closed if the lights came on. This is a short circuit because you provided a path that avoided the load. So that's called the short circuit. The result of it, the bulb didn't come on. Same thing with the open circuit, the bulb didn't come on. But they're very different. This one because you provided a less resistant path. The other because there's no path at all. So they're exactly the opposite of each other, but the result's exactly the same. The light doesn't come on. Does that make sense? So short circuits are really more dangerous because they can lead to a fire. Because too much current is going to go through that wire. That's why I just did it for half of a second, because I didn't want the wire heating up and burning something out.
So
Say again?
it says the ones that are brighter than it's the opposite of question 2. So would the answer be the opposite of this? Because there's less resistance?
Okay. You said, were those the only 2 that they were brighter?
Brighter than normal? 6, 8, and 30? Yeah.
Yeah. And notice what's true about 3, 6, and 8. Look at the diagram. Look what we got. 3, 6, and 8. What you notice about all 3 of them. and those three have in common? 3, 6, and 8. 1, 2, 5, and 7 don't have.
Oh, the lane.
Oh,
The
twice
battery.
the power, twice the voltage.
Yeah.
Okay, so they had greater voltages, and that greater voltage had a path to a single bulb. Here you had a greater voltage, but it had to go through 2 bulbs. So greater voltage and a single path to each bulb.
So for this one, it's the opposite. The bulbs are parallel, so they went on the same series. So when one was removed, the
Okay.
current still stayed on the other.
Yeah, exactly. Because in parallel, there's always a path. Still a path open.
You have to,
Okay. Sorry.
for number 6, you have to say that a battery is needed. What is this line called?
A pathway.
So we need a pathway. Do we need both pathways?
You need some pathway for the light to come on. You need a complete circuit.
Okay, just
Yes.
a complete circuit.
A complete circuit will work, or a completed pathway. You see, this had a completed pathway, but not through the bulb. Okay, because you provided a alternate pathway.
So it's a complete pathway.
Right. And a power. You had to have voltage. See, what the voltage is energy for charge, so you have to provide some energy to it. That's the voltage. You have to have a complete pathway for it to travel, and basically you needed a load. I mean, you have that load, you know, something in there to use that energy. Otherwise, like one that skipped over, nothing was going to use the energy. It just kept flowing and that was going to heat up. Ultimately, it would have bubbled the wires.
And we need a bulb.
A bulb would be, or a load, either one. Say this again. Oh, now that's your answer. You just have to answer it, but
I'm just the list. She said, I think that one doesn't say explain.
Oh.
So you can say circuit 1.5. And then this one, I just listed battery, complete pathway, voltage, and voltage. Now I give you So 7 can't be necessarily wrong.
It can be wrong with our opinion.
what's that? Yeah. The only way it can be wrong if you don't answer it.
Oh, okay.
Then you get nothing for it.
Okay.
But if whatever you think, it can be positive, negative, neutral, but you just need to answer it.
Number circuit 2 and 4. And then they are in series with each other. When one bulb is removed, they act as one on the same side. So they may go out. So number 5, circuit 5, 6, and 8. bills are parallel, which made them not on the same series.
PHY202 which makes me laugh.
Which made them not on the same series. So the current only works for one goal. Such a simple, short and sweet.
What's the last time? See, wait, sure.
Yeah, right. I mean, that wasn't bad. It was kind of interesting. I guess that's the only reason why I actually like, okay, because I'm interested. Only part of it that actually. See, it'll be messed up if you go and try to see it. Somebody took a picture. All right. Oh, and here's my test and lab work from last time.
What's up now? Oh, okay.
My other lab and my
Right.
test score.
Okay, great.
It was nice doing business with you.
All right.
Nice doing business with you.
All righty.
Peace out. Have a good night.
Thank you. You too. Have a good weekend.
You too.
And we'll see you on
Wednesday.
Wednesday.
Yes.
I will be here Tuesday.
You will be Tuesday.
I mean, Monday. I won't be here Tuesday.
I don't know you. I might be out of town.
Same as do I.
Yeah, you better go live it up. Off some fireworks.
So, go to the